A 12 volts 24 watts kettle, that is the rating or the power rating on the kettle, that is 12 volts. It operates on 12 volts and then it gives a power of 24 watts. It's connected to a supply of 12 volts. The internal resistance of the supply is negligible. And then a 7.1.1 define resistance. Resistance is defined as a material's opposition to the flow of charge, and that is it for that one. We can proceed. And then 7.1.2 calculate the resistance of the kettle. So to do any calculation, we must first find what information do we have about the kettle. We know that this kettle is rated 12 volts 24 watts. That means it operates on a 12 volts, and then its power is 24 watts, and it is connected to a source of 12 volts. That means it is operating on its voltage as indicated on the kettle. So we have information about the voltage and then the power, and we have to calculate resistance. So let's check from the formula sheet and see which formula will be appropriate. We are giving power, and then we have voltage and then the resistance. So here we have we don't have time. Power, voltage, and resistance. Power, voltage, this is power, this is voltage, and then this resistance. So this formula will fit what we are about to do, and so we choose it, and we say that power is equal to voltage square divided by the resistance. So what is the power? We can go back and then look at it. The power is 24 watts, and then the voltage is 12 volts. 12 volts. So we substitute this into the formula, and then we have a power of 24 watts is equal to voltage 12 square divided by resistance. And then when we make R the subject of the formula, we get the resistance to be 6 ohms. Then let's read the next question, and that is in the circuit represented below, the battery has an EMF of 24 volts and an internal resistance of 3 ohms. The heater, now this is a battery with a 24 volts EMF and then internal resistance of 3 ohms. Then we see a heater connected in parallel with a 30 ohm resistor, and then there's an ammeter that reads the current going through the heater, and then we have another ammeter A1 which reads the current going through the battery or the total current of the circuit. So we see a parallel section here because the current divides into two. Part is going through this ammeter, and then the other part is going through this 30 ohm, and then they meet here, and they both move through this resistor, which we call a variable resistor. Variable means that the resistance can be changed while this circuit is switched on just by adjusting a knob or a slide. So let's read the question fully to understand what is going on. The heater has so in the circuit represented below, the battery has an EMF of 24 volts and an internal resistance of 3 ohms. The heater has a resistance of 10 ohms, we've seen that already, and the fixed resistor has a resistance of 30 ohms. This one is fixed, it is not changing. The variable resistor R can vary between 0 ohms and 15 ohms. So this one we can change, we can set it to 0, we can also set it to 15, and we can set it to any value between 0 and 15. Ammeters have 0 resistance, and what it means is that no work is done or no voltage is dropped at the ammeter. And the voltmeters have indefinite resistance. That means they have very high resistance, which means that current does not go through the voltmeter. When the variable resistor R, this one, of has a resistance of 4.5 ohms, that is when it is set to, remember this one is variable, it can be set between 0 and 15, and now they are saying that when it is set to a value of 4.5, calculate the effective resistance of the external circuit. Now, when I say effective resistance, it is the same as saying the total external resistance. Effective means the total or the, the sum or the working resistance of the circuit. So what we are going to do here is to find the total resistance of this circuit. And what we see here is what? A parallel section in series with this variable resistor. So we have a parallel series combination. And what we do is first we put this parallel total together, we put it together, and then we use the series, and then whatever we get from the parallel we add it to this one, and then we get the total external. External means the resistors that are outside the battery, not, it does not include this 3 ohm. So we can look at how that is worked. And then we start first by adding the parallel together. Use the parallel formula, which is this one over R parallel is equal to 1 over R1 plus 1 over R2. And here, since we have only 2 resistors in parallel, we only use the formula like this. That is 1 over Rp is equal to 1 over R1 plus 1 over R2. And then 1 over R parallel is equal to the 2 resistors in parallel are the 10 ohm and then the 30 ohm. So when we add them together, you enter the fraction editor on your calculator, and then you enter direct 1 over 10 plus 1 over 30, and then after that you use the x raised to the power negative 1 button to turn it upside down, and then when you press, you change a fraction to a decimal, it gives you a total parallel of 7.5 ohms. Then the total external resistance or the effective resistance of the external circuit is going to be the parallel plus the resistance of the variable resistor, which is this one. That is the total for this section plus this 4.5, and we get a total of 12 ohms. Then we look at the next question. It says state Ohm's law, and then this one is a statement of a law. We just state it as it is, which is the potential difference across a conductor is directly proportional to the current through the conductor, provided temperature remains constant. So we go to the next question, which is 7.2.3. Calculate the current measured by ammeter A1, this ammeter. Now, what we need to know is that this ammeter is measuring which current? Is measuring the current that is passing through the battery, which is the total current of the circuit. It means that this current is influenced by both the external resistors and what? The internal resistor. Remember, we define resistance as the opposition to the flow of electric charge. So there is an opposition to the flow of the current. So we need to include all the resistors in calculating the current. So the formula that will be appropriate will be the one involving all the resistors, and then the EMF, which is EMF E is equal to the total current plus multiplied by the sum of the external and then the internal resistance. So we quote this formula as it is here. We write it down. EMF is equal to I. Don't be worried. EMF can also be written like this. So it's I times R external plus R, and then the battery EMF is 24 plus the total current plus total external, which we found in the 7.2.1, plus the internal, which is 3. And then when we use our calculators here, we get the total current to be 1.6 amperes. And then we go to the next question, which is 7.2.4. Calculate the current measured by ammeter A2. That is the current that is going through the heater. Now there are two. There's more than one way that we can get this current. Remember, now we know the total current here to be 1.6 amperes, and then what we can do is these two lines, or these two resistors, the 10 ohm and then the 30 ohm, are current dividers. And then how do they divide the total current? They divide it inversely proportionally. That means that the resistor with a higher resistance will take a low proportion of the current, and then the one with a lower resistance will take a high proportion of the current. So the total proportion here will be 10 plus 30, which is 40. So these two resistors will divide the total current into 40 parts, and then one of them will take 30 parts, and then the other one will take what, 10 parts. Now which one take 10 parts is the higher resistance path will take only 10 parts, and then the low resistance path, which is a path of the heater, will take 30 parts of the 40. So we can say that the current through the ammeter, that is where, or current through I10, which is through the 10 ohm, is the higher proportion, because that is a lower resistance over the total portions of the times 1.6, and that gives us 1.2 amperes. Now if we don't do it simply like this, then we can use Ohm's law. That is R parallel is equal to V, R is equal to V over I. And how does this one work? We know that these two resistors, that the heater and then the 30 ohm resistor, they are current dividers. So the voltage here is the same. They have the same voltage. So what we have to do now is we calculate what we call the parallel voltage, and then when we get the parallel voltage, we use the voltage and the resistance in Ohm's law, and then we find the value of the current that is going through the heater. So when we do that, we are going to say the parallel resistor is equal to the parallel voltage divided by the total current. So remember, this parallel resistor is the addition of the two parallel resistors. So when we are talking about current, it should be the total current there. And then we say 7.5, that's what we found here, is equal to the parallel voltage divided by the total current 1.6. And then when we make the parallel voltage the subject, we get 12 volts. Then this formula, this same formula, which we call the Ohm's law formula, we can write it as V is equal to IR by making the voltage the subject of the formula. That is V is equal to I times R. Then the voltage of the parallel, which is 12 volts, is equal to the current times the 10 ohm, which is the resistance of where we are looking for the current, that is A2. Remember, to calculate the current measured by ammeter A2, and we get, when we divide through by 10, we also get the current to be 1.2 amperes. So we see that either you do it simply like this or like this, it will give you the same answer. Never mind about the max. Even if you do it this way, you will still get your total max. You do it this way, you get your total max, unless you are told that you must use this method. If you are not told to use any specific or any particular method, use any method that is applicable, and then you still get the total max. Then let's look at the final or the next question. The variable resistor is now adjusted to have a higher resistance. Remember, it is set to 4.5. So it means this time it is greater than 4.5. And then, will the heater dissipate more heat or less heat or the same amount of heat? Explain your answer by making use of your suitable equation. Now, what is heat? Heat is about electrical energy. And the electrical energy depends on what? The power. Remember this formula. Energy is equal to VI times the time. VI is power. VI here is power. I square R is power. I square R here is power. V square over R is power. V square over R is power. So given the same time, the electrical energy will depend on what? The power of the resistor. So anything that affects the power will actually affect the heat or the electrical energy that resistor will be able to dissipate. So let us look at what we have there. And then they say, will the heater dissipate more heat or less heat? Now let's see how this change affects the power or the voltage. And then remember, the elements of power is voltage and current. So when we increase resistance this side, what happens? Let's remember that this parallel section and this variable resistor are voltage dividers, and they divide the total voltage proportionally. That means the higher the resistance, the higher the proportion of voltage they will take. So when you increase resistance this side, it means its proportion, the proportion of the voltage that will be taken by this variable resistor will increase. So if that happens, it means this will now take a lower proportion. So voltage here will decrease. And that means that if voltage decreases, it means that the power will also decrease. And then when power decreases, it means there will be less heat. And we can also look at it this way in terms of current. When you increase resistance this side, the current that is going through the battery, which is the total current, will decrease, because we know that current and resistance are inversely related. The higher the resistance, the lower the current. So we are going to have a lower current. It means this 10 ohm and 30 ohm now have a lower current to divide, to share. And that means that this side is going to receive what? A lower current. And then in the same way, the power will also be less. So let's look at how we put it on paper. We say there will be what? Less heat, because the current decreases at the parallel section, or the voltage decreases. And then they say use a relevant formula, which is power is equal to I square R. That is for current decreasing, or voltage decreases is we say V square over R will decrease. And that is how we answer this question.